Good morning, everyone. Can you hear me?
Yeah.
Yes.
Okay, let's wait for a few more minutes. We're assembling and then we'll start. Good morning once again. Welcome into our Analytical Geometry and Linear Algebra lecture. So today we'll continue our study of second-order curves. You remember we introduced second-order curves or conical sections or conics for short in the last lecture. We explained why they're important. That first of all, they were studied by ancient Greek mathematicians just out of abstract interest, but then it turned out in the 17th century that the planetary motions occur along the orbits, which are precisely conical sections, and then they became immediately greatly important for astronomy, physics, and nowadays for spaceflight mechanics as well. So they indeed warrant a very detailed study. We introduced classification of those curves by really taking a cone and then performing sections of this cone with any plane inclined to the cone axis. So we're obtaining, by increasing the inclination angle, we're obtaining first a circle, then an ellipse, then in some intermediate case, when the plane was parallel to the side of the cone, we got a parabola, then we got a hyperbola, then in some degenerate cases we could get a pair of straight lines, a single point, or even in one very degenerate case, just a single straight line. So all those geometrical objects are conical sections. Most of them are second order curves, although if it is a single point or a single straight line, then it is arguably, well, a single straight line at least is a first order curve as a very degenerate case. Okay, so today we will continue to study in more detail the geometry of those objects, and in particular we are interested in the geometry of the ellipse. I will share my screen and we'll go. You can see the whiteboard, all is fine?
Yes.
Okay, so ellipse to begin with. By far the most important second order curve, because most of orbits of solar system bodies, for example, are elliptical orbits. We are not studying the kinematics of orbital motion yet. That will be done in the last three sections, in the last three lectures. For the moment, we are only considering the geometry of the ellipse. So the canonical equation of the ellipse we have already seen, and it is simple and easy to remember. So if we draw up the xy coordinate plane, then it is x squared divided by a squared plus y squared divided by b squared equal to 1. And typically it is depicted like this. Yes. Now, by substituting, for example, y equal to 0 into this equation, we immediately get that x equals to plus minus a. Therefore, the intersection points of our ellipse with the x-axis have x coordinates being a and minus a. By substituting the same way, x equal to 0, we got plus b here and minus b here. It is just by convention that we depict our ellipse in a way that, in this particular case, that a is greater than b. So by convention, we would always do that. And then there are some special terms. So if a is greater than b, then a is called semi-major axis. Because a is greater than b. b is called semi-minor axis. Obviously, in the opposite case, if b is greater than a, we would have a picture like this. But then, just to preserve our terminology, that A is semi-major axis, and therefore it must be greater than A. In that case, we would perform a rotation of our ellipse, for example, by pi over 2. About rotations and other transforms, we'll talk later, I think, in the next lecture, and we will get our axis, our ellipse in this canonical form with a greater than b, and then basically these names, semi-major axis and semi-minor axis, will be correct, because major should be greater than minor. It's interesting that look at the names. Why semi? Semi means half. So the major axis of the ellipse is from minus a to a. So that's major axis, which is 2 times a. And obviously minor axis is 2 times b. Semi-major and semi-minor means half major, half minor. Okay. What other interesting things we can do with the ellipse? The most important property of the ellipse is the focal property, which we'll establish now. So apart from the points we have seen so far, there are other 2 points which are called foci in plural, focus in singular. So there are 2 points located on the semi-major axis, on the x-axis. For the moment, we don't have the coordinates of these points, but we'll find them very shortly. Symmetrical with respect to the center. Center of the ellipse in this case coincides with the center of with the origin of our coordinate system, O. So let's say the coordinates of these points are L and minus L, which satisfy the following property. Take any point xy on our axis, on our ellipse, and consider the distances from this current point xy to the foci. That's the first focus, that's the second focus. Then the sum of these distances, let me denote this focus f1 by f1, and this one, for example, by f2. Then, and this is the current point, let's say just current point m. Then the sum of the distances mf1 plus mf2 is constant. Doesn't depend on m. And if it is constant, then it is very easy to see. We haven't yet proved that it is constant, and what are these points f1 and f2. We haven't proved it yet, but we can immediately see that if it is constant, then it is equal to what? Suppose that the m point is here on the semi-major axis. Then the sum of the distances would be, in particular, so we have f2, f1, and, for example, the point m here. It would be equal to, let's say this is point m1. It would be m1 f2 plus m1 f1. Okay, m1 f1 is precisely this distance, m1 f2 is that one, m1 f2. Therefore, actually, it would be equal to m1 f1 twice plus this constant distance between f1 and f2, which is actually 2 times L. But due to the symmetry, we can also say that this distance would be equal to, yes, this uh, fixed one, f1, f2, plus m1, f1, as it used to be. But for the second m1, f1, we will take this distance. Suppose that this is point m2, plus m2, f2, which is equal to m1, f1. And therefore, altogether, it is equal to 2 times a. So if indeed we have such 40 or focal points, f1 and f2, that this focal property holds, then this constant must be equal to 2 times a, so equal to the major axis of the ellipse for all other points. So, okay, let us see. We will try to, starting with this equation of the ellipse, we will try to see, or maybe other way around, we'll start with this property and try to get the equation of our ellipse and try to see how this L distance is connected to A and B. So for an arbitrary point M, we would have that the square root of the distance, and this distance is between x and y, xy, and obviously this point is L0, this one is minus L0. Therefore we have x minus L squared plus y squared plus square root x plus L squared plus y squared must be equal to 2 times c. Okay, let me stop here for a second and ask if everything we have discussed so far is clear.
I have a question.
Yes, please.
In equation m1 f2 plus m what f1.
M1 F2 plus um, interesting point. Yes, let's see. M1 okay. MF1 for any point MF1 plus MF2 is constant. This must be M1 as well, but if we consider in particular point F1, M1, then M1 F1 plus M1 F2, just in the opposite, yes, M1 F2 plus M1 F1 must be equal to the same constant. Take xy here, this is a point M1, M1 F1 plus M1 F2 must be equal to the same constant, and then it is equal to 2 times M1 F1 plus F1 F2, or equal to F1 F2 M1 F1 plus M2 F2. Excuse me for my handwriting, this is just M1. Okay,
Okay, thank you.
thank you. And then we get this equation. Okay, what should we probably do about this. We have two square roots in the left-hand side. We can a typical way, we can either square up the left-hand side, but then we get obviously another square root. A very typical way of how we deal with this equation is that we move one square root into the right-hand side and then square up the sides. Yet we'll get obviously yet another square root anyway. X minus L squared square root plus y squared, so let's write that, equals to 2 times A minus maybe I retain plus in the left hand side, move minus into the into the right hand side. X minus L squared plus y squared. Now we square it up and we get x plus L squared plus y squared equals to 4 times A squared minus 4 times A square root x minus L squared plus y squared plus x minus L squared plus y squared. Obviously now by expanding these terms, we get y squared dropped in both left hand side and the right hand side. X squared and L squared are dropped as well. So we get only 2 times XL in the left hand side equals to 4 times A squared minus 4 times A square root x minus L squared plus y squared. Again, x squared, L squared, and y squared are dropped. Minus 2 times XL. Okay. Now, moving, obviously, we'll get 4 times XL. Moving all terms without the square root into the left-hand side. For example, we would get, and dividing by 4, we would get something like, and changing the sign, would get so A squared minus XL, A squared minus XL equals to square root of x minus L squared plus y squared. Correct? Please check.
And times A, the square root should.
Yes, times A. Thank you. Obviously times A. Fine. Now constructing a square once again. A squared minus 2 times A squared L, A squared LX plus x squared L squared equals to A squared x squared minus 2 times XL plus L squared plus y squared. Great. Now,
Sorry, A in power of 4 in the left hand side.
thank you. A to the power of 4. Yeah, thanks. A to the power of 4 minus 2 times A squared L x plus x squared L squared. Yes, you're right. A squared x squared minus 2XL plus L squared plus y squared. should be okay now. Now, fortunately, the linear term minus 2 times a squared lx is dropped. Otherwise, we would have a linear function of x, linear term in x here, which we don't like. And we get a to the power 4 plus, by the way, yes, plus x squared L squared equals to a squared x squared plus a squared L a squared L squared plus a squared y squared. Now collecting all the terms in one side, we get the following. So with x we have a squared and L squared. Therefore, a squared minus L squared, a squared minus L squared, x squared plus a squared y squared equals to a squared times a squared minus L squared. Fortunately, from our drawing, we assumed that indeed L as a focus lies inside our ellipse, so L should be less than A. At least that's what we assumed. And because L is less than A, then this coefficient is indeed positive. Otherwise, we wouldn't get an ellipse, right? Okay. So now, dividing by the left-hand side and the right-hand side by the product of a squared minus L squared, we finally get x squared divided by a squared plus y squared divided by a squared minus L squared equals to 1. So this is indeed the ellipse. And from this, compared to our original equation, we immediately see that b squared for semi-minor axis is equal to a squared minus L squared. And actually, that's very easy to see from our original drawing as well, because obviously, easy or not so easy? No, probably not so easy. We'll see it later when we introduce the eccentricity, but for the moment, yes. So B and L are connected by that property, which defines L, actually. So if we place, which means that L is a square root of a squared minus b squared. So if we place, and this is the distance, L is O F 1, 2. If we place our 40 at this distance from the center, from the origin, which is a square root of a squared minus b squared, then we would have indeed this nice property of the ellipse. This, by the way, results in a very easy geometric way of how we can plot an ellipse and how we could really do it before the advent of the computers when we plotted them, when we started plotting them just on a computer screen using computer graphics. So if we draw two nails into our disk here in points F2 and F1, okay, then take a chord or a thread of the length 2 times A, and then take a pencil, get this chord stretched, and then follow a full cycle, then our pencil will draw an ellipse. All right? This is a well-known, historically well-known way of drawing up an ellipse using a chord, two nails and a chord. Okay. Now, a very important property which we'll introduce. Let us introduce the following parameter, which is the eccentricity of the ellipse. You will immediately see why it is useful. Eccentricity, eccentricity is precisely the relationship of our L and X. We said L is less than A, sorry, L and A. L is less than A, obviously greater than 0 in any case. Well, not necessarily greater than or equal to 0. Then the eccentricity is precisely the ratio of L to A. And for the ellipse, the eccentricity is between 0 and 1. In this particular case, not including 1. Although we'll consider the degenerate case of 1 as well. If the eccentricity is 0, then L is 0. If L is 0, then as you can see here, B equals to A, which means we got what?
Circle.
Yes. So eccentricity being equal to 0 implies B equals to A, and this is a circle. The ellipse is just a generalized circle with eccentricity being any value between 0 and 1, for the moment not including 1. Okay, in that case, we can immediately see that obviously L is equals to A times E. Why it is a good thing? Because A defines the overall size of the ellipse. All right, so that the major, semi-major axis, which define the overall scale. Where the eccentricity is a relative parameter which describes the shape of the ellipse, in this case, the obliquity of the ellipse. From this, we immediately see that b squared equals to a squared minus a squared e squared equals to a squared 1 minus e squared, and therefore b equals to a times square root 1 minus e squared. So that's the relationship between minor and major semi-axis of the ellipse and its eccentricity. So far so good. Let us now consider a little bit more geometric properties here. So first of all, there are so-called perifocal distances. it will be very important when we study in particular the orbital motions. I can tell you straight away that if our ellipse is a planetary orbit around the sun, for example, then the sun is not located in the center in O point here. The sun is precisely located in a focus. So for example, in F1. And that's why it is very important to understand the relationship of various parts of the ellipse compared to F1. So first of all, maybe I will draw another picture so it will be easier for you. There will be a very important parameter, which is the distance F1 to the point M1, which is the so-called pericenter of the ellipse. That's the nearest point of the ellipse to one of the 40. So let's assume that F1 is the main one and consider those distances. So once again, now I'm much more interested in the focus than in the center of our ellipse. So the focus is somewhere here. So that's our F1. The origin is still here. This distance, let's suppose our M1 point, that distance, F1 M1, is obviously A minus O F1, which is AE, which is A times 1 minus E, which is called pericentric distance. The pericenter itself is M1. Although it is more correct to call it perifocal point, but we'll call it pericenter. Whereas the distance to M2, F1 M2, very easy to see. What is? It is A plus AE. It is equal to A1 plus E. Finally, if we consider this distance from F1 to our point on an ellipse in the orthogonal direction, M3, then F1 M3, and by the way, this is called apocenter distance, apocenter. Then this would be, how can we compute this? The easiest way, let's call it P. The easiest way, by the way, to compute it would be probably to consider the equation of our ellipse in the original coordinate, because this is just the y coordinate in the original equation. So where the x is here, so we have x squared over a squared plus y squared over b squared equals to 1. For the point M3, we have x equals to, obviously, OF1 AE, y equals to this yet unknown P. You agree with that? And therefore, E squared, simply, plus P squared divided by B squared, but B squared is A squared 1 minus E squared equals to 1. And therefore, P squared equals to 1 minus e squared e squared. Just a second, something is wrong here. Let's check. Because for me this would be equal to a. Let's see. P squared. Or no, it's okay. A squared 1 minus e squared. In this case, is equal to 1 minus e squared. Yes, and then multiplying, no, it's okay. Multiplying by 1 minus e squared, we get p squared is 1 minus e squared times a squared. No, that's fine. And eventually, we assume that p is positive, and therefore p is just a times 1 minus e squared. Yeah, that's correct. P is the focal parameter, is a minus a times 1 minus e squared.
Excuse me, Professor. Can you please remind why our x is equal to 8e? I missed that.
Why x is equal to ap, because this is for the point M3, x is precisely OF1. And OF1, because F is a focus, is precisely the L which we have considered so far. And by definition, we introduce E such that E equals to L divided by A. Have a look a little bit above. By definition, we introduce the eccentricity in such a way that eccentricity is L divided by A. So basically what we did, let's do once again. First of all, we drew up an ellipse. We said, okay, this point M1 is A0, M2 is minus A0, right? This point is 0B, this point is 0 minus B, okay? Then we said, we introduced 240, F1 and F2, and we said F1 would be L0, where L was yet unknown, F2 was minus L0. Then then we introduced this, the 40 are not just accidental points. For any point M, we would have a property that F1M plus F2M equals to a constant. And we have shown that this constant is equal to 2 times A. Then by expanding, you remember this algebra which we did, by expanding these equations, this actual equation, we arrived at x squared over a squared plus y squared over a squared minus l squared equals to 1. From that, we immediately found that L equals to the square root of a squared minus b squared. From then, we just by definition introduced the eccentricity is L divided by A, and then our geometry takes shape. So OF1 is AE, F1M1 is A times 1 minus E, and therefore OM1 altogether is obviously A. B appeared to be A times square root of 1 minus A squared, And finally, we computed this F1 M3, which is denoted by P, and it appeared to be A times 1 minus E squared, compared to semi-minor axis B, which is A times square root of 1 minus E squared. Okay, is it clear now?
Yes, thank you.
Okay, now from those equations, it should be clear, and it is correct indeed, that P is greater than B or less than B. P is A times 1 minus E squared. B is A times square root of 1 minus E squared. So which one is larger?
Larger.
What?
B.
B is larger, yes, because 1 minus E squared is less than or equal to 1 and greater than 0. Then for those values which are in between 0 and 1, square root of x is greater than or equal to x. All right? Therefore, square root of 1 minus e squared is greater than or equal to at least 1 minus e squared itself. And therefore, we would have b being greater than or equal to p, and obviously b equals to p if our eccentricity equals to 0. Also, b equals to would equal to p if our eccentricity is 1, but this is a degenerate case which we didn't consider it yet. Okay, now the question is, can we have an ellipse? Okay, the ellipse of the eccentricity 0 is a circle. The greater the eccentricity is, the greater is visual obliquity of the ellipse. Let me call it that way. So the ellipse with eccentricity near 0 looks like a near circle. When the eccentricity increases, the ellipse becomes more and more and more, let's say, disproportional, because B becomes smaller and smaller and smaller compared than A. Correct? Now what? When E tends to 1, what would be the limiting case of our ellipse? What do you think?
Is it parabola?
In one particular case, it will be parabola, but not in this case. So suppose that parabola does indeed have eccentricity of 1, but not only the parabola, interestingly enough. So let's consider it a little bit more carefully. Suppose that A is constant. A is constant. So all our points are in fact in place. So basically we have our points, obviously the origin, M1 and M2 are fixed. M1, M2 fixed. The pericenters, pericenter and hypocenter, M1 and M2 are fixed. But eccentricity now tends to 1. What does it mean? This means that B, being the square root of 1 minus e squared, tends to 0. So our ellipse has a fixed major axis, but the minor axis tending to 0. What do we get in a very limiting case?
A line.
A segment.
Yes, yes, we have a straight line segment in that case. So excuse my handwriting. So it would be, for example, eccentricity equal to 0 is a circle. Now we have a certain eccentricity between 0 and 1. We have here an ellipse, and eventually, for eccentricity being equal to 1, our minor axis became 0. With the minor axis being 0, we got a straight line segment. So it is a straight line segment. Of the same length 2 times a. So interestingly enough, the eccentricity being equal to 1 corresponds not only to a parabola. A parabola could be obtained in a different way. If, how do I obtain a parabola actually? Well, I think study this in a little bit more detail later, but a parabola could be obtained if we fix our point F1 and we fix our point M1 and we start with a fixed focus, start increasing A. In that case, eventually when A becomes infinite, our ellipse becomes a parabola. But if the size of the ellipse is fixed, so it is still of the major axis being 2 times A, but eccentricity tending to 1 simply by shrinking B, then it becomes a straight line segment. Okay? Okay, short 5-minute break or less, and then we'll continue. Okay? Okay, back to our ellipses. Let us also consider the area of the ellipse. You can probably guess what the area of the ellipse is. For the circle, suppose that there is a circle of radius a. The area is obviously pi a squared, or as a hint, it is pi times a times a. Can you guess what would be the area of the ellipse?
Pi over times a times b.
Yes. So for the ellipse, and we'll now see why, s equals to pi a times b. How can we prove this? Well, obviously, the standard way, I believe that I already advanced in your mathematical analysis enough that you have seen integration and how integrals can be used to compute areas.
No.
No,
Not yet.
Not yet. Then this
But
you're
process.
talking about Newton-Leibniz formula, yes?
Newton-Leibniz formula, yeah, that's what I meant, yes, how an area can be computed via a quadrature, a definite integral, using Newton-Leibniz formula. Have you seen that?
Well, actually, it was in school. So I guess
It wasn't so.
I guess every Russian students at least know this formula. At least Russian students
Well,
know.
Russian students, yes, but we're not all Russians here. Then
We will introduce it in few weeks
in
because
a few weeks. So basically, yes, but we'll do a much better way without actually the use of this formula. You can see that even by very elementary means, this can be achieved. So yes, indeed. So if we have, let's say, a curve y of x for the upper part, okay, then of our ellipse, then and we know in this particular case that x is from minus a to plus a, then s can be computed as a quadrature or a definite integral using this Newton-Leibniz formula from minus a to plus a of simply y of x dx. And from our equation x squared over a squared plus y squared over b squared equals to 1, we immediately get that y squared over b squared is 1 minus x squared over a squared, and therefore y in this particular case for the upper arc, and this is obviously not the whole s, it is only s of the upper part, therefore in general it would be times 2 times that, would have y equals to plus b times 1 minus a squared, x squared over a squared, or it would be square root of b squared minus b squared over a squared x squared, or what is b squared over a squared? We have already seen that b is a times square root of 1 minus a squared. Therefore, b squared divided by a squared is nothing but 1 minus a squared, all right? And therefore, it is the square root of b squared minus 1 minus e squared x squared, something like this. So that's our y of x, and therefore the full area is 2 times integral from minus a to plus a square root of b squared minus 1 minus e squared x squared dx. But we'll not try to compute this integral. There is much easier way of how we can reason actually about the area of our ellipse. Consider the following. Let us consider, and we'll use this argument one more time when we study the Keplerian orbital motion. So remember this point, it will be used once again. So consider another coordinate system with the same x, but instead of y, we will introduce another coordinate which is, let's say, called eta. And in this coordinate system x eta with the same origin, we will consider really a circle of a radius a. So we have x squared plus eta squared equals to a squared. Okay? And now we consider our coordinate system such that it is actually a compression of the coordinate system we have seen so far along the vertical axis. So basically now instead of x eta, we have xy, but we want to have an ellipse of semi-major axis being a, but semi-minor axis being b instead of a as well. So this is minus a to plus a. This is minus a to plus a as well. But this point is b, so y equals to b should correspond to eta equals to a. Therefore, basically the transform between the two systems is y, x is the same, but y would be equal to what? Eta b over a divided by eta, all right? So when eta equals to a, then y is only b. So this is b over a, or we can say b over a is obviously square root of 1 minus c squared times eta. This type of transform. Okay, so what happens in that case? We can consider the area of precisely how this actually Newton-Leibniz formula is derived and how we can compute the area of a geometric object using the integral. What do? We split the x-axis into infinitesimally small intervals. All right? And for each interval of some infinitesimally small size, let's say dx, we compute the area of the elementary strip, which is, because dx is very small, the strip is supposed to be rectangular, And the area of this rectangle is precisely y, let's suppose a current point x, y of x. In this particular case, it is eta of x times dx. And by the way, so you shouldn't be surprised. Let's verify this. If we had an equation x squared plus eta squared equals to a squared, and then we have this transform that y is b over a times eta, or equivalently, eta is a over b times y, then what would be the xy equation of our curve? We have x squared plus, instead of eta squared, we have a squared over b squared y squared equals to a squared. And from this, it immediately follows that x squared over a squared plus y squared over b squared is 1, and it is indeed an ellipse. So what used to be a circle in eta, in x eta coordinates becomes an ellipse in eta, in x y coordinates. So I would better not to confuse you. Let's say this is eta and this is y. The axes are same up to a direction, but different up to a scale. So that's the relationship between them. By the way, when we studied various orthogonal transforms in the first part of the course, we did not consider this type of transforms. You remember, we studied orthogonal transforms and possibly, which are possibly rotations or mirror symmetries. And all those transforms, that's very important, they preserved the distance between the points, they preserved, because they were orthogonal, the angles, and obviously they preserve the areas. Orthogonal transforms preserve the angles and areas. Distances, angles, and areas. Where this transform, this relationship between y and eta, is not a kind of orthogonal transform we have seen so far, right? This is a scaling transform. Scaling transform. Okay? Because this is a scaling transform, the area is not preserved. So what happens actually when we move from eta to y, that any vertical strip which was of height eta becomes of height y as a result of this transform, which is b over a times eta. Therefore, if the whole area is basically this integral, which is the sum, suppose that we have many elementary intervals here, so it is a sum for all intervals. Dx, which is the base of each interval, let's say dxi, times eta of xi, and that was equal to the original area of, well, not of a circle, but of the upper semicircle. So that was p over 2 a squared. But now, instead of eta of xi, everything else is the same, but instead of eta of xi of this strip, we consider y of xi, which is less, which is a over b, sorry, other way around, for y it is b over a times eta over xi. Therefore, sum over same intervals dxi, but now b over a eta of xi, factoring out b over a, would be equal to pi over 2a squared times the scaling coefficient in the vertical direction b over a. And therefore, we get pi over 2 ab, from which it follows immediately that the area of the ellipse is indeed pi ab. Okay? Is this more or less clear?
No,
Yes.
Yes or no?
yes, yes.
Yes, more or less. Okay. And finally, what I would like to introduce for today, we did not study parabolas and hyperbolas in that much detail, but we'll consider it next time, and then we'll also consider general transformations of our coordinates when we can shift the origin, rotate our coordinates. And obviously, if we do that, then our ellipses become ellipses, parabolas are still parabolas, hyperbolas are still hyperbolas, only the equations are different. So we would need to recognize them in rotated, shifted, otherwise transformed coordinates. But for the moment, we will do the following. The final thing I would like to do is to consider parametric equations of the ellipse and equations in the polar coordinates. So basically, if we start with the original equation, xy, and we have x squared over a squared plus y squared over b squared being 1, obviously, it is quite inconvenient to express x and y, x, y, y, or y, y, x. We have already done this. So basically, we can say that for any given x, y is plus minus square root of plus minus b square root of 1 minus x squared over a squared. But so that's basically plus corresponds to the upper arc of our ellipse, obviously, minus corresponds to the lower one. But there is another way of how we can represent the ellipse. You remember when we studied straight lines or planes in 3D, we had parametric and non-parametric equations of lines and planes. You remember? So what kind of this equation, if we consider the ellipse, is it parametric or non-parametric? You remember, for example, for a straight line, we had something like this. Parametric equation was the following. X, y, z as a vector of a point on this straight line was equal to x0, y0, z0 plus some parameter t times ABC, where ABC is any kind of directing vector of this straight line, or R was equal to R0 plus T times this directing vector D. So it was parametric because the parameter was precisely T. T was any parameter, real number. Whereas a non-parametric equation of a straight line was the following, because t is the same for the expressions in x, y, and z, we could say that x minus x0, by the way, x minus x0 divided by a is actually that t, but we don't write t here. We just assume it is t. X minus x0 over a equals to y minus y0 over b equals to z minus z0 over c, and yes, equals to t, but we do not write t here. Assuming, of course, that a, b, and c are greater than 0, because if not, you remember we had a lot of degenerate cases. So that was a non-parametric equation. Comparing the two, parametric and non-parametric, this equation of the ellipse, is it parametric or non-parametric?
Equation of ellipse?
For the ellipse, yes. So we have
not parametric.
non-parametric. This is a non-parametric equation. It is just an equation which connects together x and y coordinates of the ellipse, but there is no parameter on which both x and y would depend. But it is very, very easy to derive a parametric one. A parametric equation, you can probably guess or you can recognize it immediately, that if we say x equals to a times cosine t, y being b times sine t, then x squared over a squared is cosine squared t, y squared over b squared is sine squared t. Therefore, the sum of them is 1, identically, all right? And therefore, our equation of the ellipse holds. So x being a cosine t and y being b sine t is precisely a parametric equation of the ellipse. Which is a very convenient one. Obviously, this point corresponds to t equals to t equals to what?
0.
0. This point is
Pi over 2.
pi over 2, and therefore this is 3 pi over 2. Sorry, this is pi. This is 3 pi over 2, or minus pi over 2, and so on. A more interesting question is the following. Can we really say that in this case, t is the polar angle, that this is geometrically t, that for any point xy, this is precisely the t. So if this is, for example, the radius vector of our point, then r is the square, r is the square root of x squared plus y squared, and then x is r. Let me call it just phi initially. That x equals to r cosine phi, y equals to r sine phi. And in this case, phi is again between 0 and 2 pi. But the question is, t is the same as phi or not? We can see that they coincide with in the points t equals to 0. Yes, it corresponds to phi equals to 0, obviously. T equals to pi over 2 corresponds to phi equals to pi over 2, and so on. But whether t and phi are geometrically the same everywhere remains to be seen. And that's what I would like to leave to you as a home exercise. So in the next lecture, I will ask you to prove or disprove that t and phi are same. So a parameter t, which is used in our parameterization, although it appears that its geometric meaning is something like the polar angle, but in fact we are not completely sure. It may or may not be the same as the polar angle if we introduce the polar coordinates, where phi is precisely the angle between the x-axis and the radius vector of a given point. Whether phi and t are the same, that's a question which I leave open, and it remains to you to check, to prove or disprove whether they're equal. Okay? Looks like in point 0 pi over 2 pi and 3 pi over 2, well, they're the same. When they're the same everywhere, may or may not be the case. And what is really important is the following. We do not have time to complete it now, but we'll take time to complete it in the next lecture. The ellipse equation in polar coordinates. What do I mean? In polar coordinates, but not in the polar coordinates as we introduced before. In polar coordinates, over the focus. So we do the following. That was our original xy equation. So that's x and y. But now we know there is a focal point. So that's our point F1. So now what I do, I introduce new coordinates, first of all, moving the origin into this point. So the new origin, O prime, would be F1, and the new coordinate system will be, let's say, xi instead of x, eta instead of y. So we had x squared over a squared plus y squared over b squared was equal to 1. Now we introduce translation of the origin. The new origin is precisely in our focal point F1. So obviously y is the same as eta. So we can say eta is y. Now can you tell me please how xi and x are connected? If we move our origin along the x-axis into the point F1. You remember that OF1 is L, which is A times E. You remember?
Yes, yes.
So how do we connect x and xi? X equals to AE becomes xi equals to 0 because this is F1. Okay? Therefore, xi equals to what?
AE minus x.
Not minus x because they are in the same direction, so they would have same sign. So x and xi, they have a different origin, but they both increase. Other way around, xi is x minus ae in general. The bigger x, the bigger xi. They have same sign, but x equals to ae corresponds to xi being 0. Please have a look, that's very important to understand. That's simply a one-dimensional actual translation of the origin. Eta is the same as y, but xi and x are connected by a very simple translation. Xi is x minus ae. Or we can say that other way around, x is xi plus ae. And therefore, xi plus ae squared divided by a squared plus, instead of y, we now write eta squared divided by b squared equals to 1. Okay? So that's what we did. We wrote this in new coordinates where the origin is now in the focus of our ellipse. But that's not all what we want. Now we introduce polar coordinates, but here, polar coordinates with the origin in our F1. So for any point, now point psi eta in the ellipse, that's the radius vector, and this is the polar angle, phi. So now we say psi is r cosine phi, psi not x. Eta is r sine phi. So we introduce polar coordinates here. So what we would like to do is to derive the equation of our ellipse in the form r of phi. So what would be, if the origin is now in the focus, what would be the relationship between our radius vector of an ellipse and the polar angle if the origin of our coordinate system is in a focus? We will, you can try, by the way, you can try it as a home exercise, but we'll begin our next lecture with this derivation before going further. That's a very important thing. Okay, so we are done for today. Any questions, please? Not yet. Wonderful. Thank you very much. Thanks to everyone.
Excuse me, I have a question.
Yes, please.
And do we have a test today?
Whether you have a test today, I honestly do not know, but presumably, well, really don't know.
Okay, thanks. Goodbye.
Okay, thank you. Thanks.
Goodbye.
Thank you. Goodbye.